Hi, this is Dr. Goldstein, and I am going to give you a quick intuitive introduction to what is called the instantaneous rate of change of a function. So before we talk about instantaneous rate of change, recall that the average rate of change of a function, f of x, on the interval from a to b is defined as f of b minus f of a divided by b minus a. Now, one way of interpreting this is as the slope of the line segment between the points A, f of A, to B, f of B. So if we look at this graph that I have in the lower corner, we have this point A, f of A, it's right there, and we have the point B, f of B, and what we're saying is that the slope of this line segment between them, the slope of this line, is the average rate of change. So here the slope is the average rate of change, which I'll abbreviate like that. All right, so let's look at what happens to the average rate of change on various intervals, and we're going to look at a particular function. So this is f of x equals x squared plus 4x, and we're going to look at the interval from 1 to 3. So here, if I want to look at the average rate of change of this function on this interval, I look at f of 3 minus f of 1 divided by 3 minus 1. When I plug 3 into f of x, I get 21. When I plug 1 in, I get 5. And so I end up with 16 divided by 2, which is 8. So I know the average rate of change of this function on this interval is 8. If I look at another interval, let's say that I look at the interval from 1 to 2. So this is a slightly shorter interval. If I look at the average rate of change on this interval, I have to compute f of 2 minus f of 1 divided by 2 minus 1. So when I plug 2 into f, I get 12 minus 5 over 2 minus 1. So this is 7 over 1, which is just 7. So visually what we've done is we've taken this right-hand point, this 3, and we've brought it 1 unit closer. Well, what if we bring it a little bit closer? So on the interval from 1 to 1.5. So now my interval is only 0.5 long. So I compute f of 1.5 minus f of 1 divided by 1.5 minus 1. So this is going to end up being 8.25 minus 5 over 0.5. And when I plug that into a calculator, I get 6.5. Well, and what if I make my interval even shorter? What if I only go from 1 to 1.1? Well, and let's do one more after that. What if I go from 1 to 1.001? So I've made my interval very, very short. So here I'll calculate f of 1.1 minus f of 1 divided by 1.1 minus 1. So this is going to be 5.61 minus 5 over 0.1, which is going to give me 6.1. And on my last very teeny interval, I have f of 1.001 minus f of 1 over 1.001 minus 1. And this ends up being, I just plug this into my calculator. I haven't even bothered to write out all of the other numbers. This is 6.001. So what we see is that as the interval gets smaller and smaller and smaller, my numbers seem to converge on 6. So the idea is that as the interval gets shorter and shorter toward x equals 1. So I'm getting closer and closer to just plugging in the number x equals 1. The average rate of change seems to approach 6. You could imagine if I made this interval shorter and shorter and shorter and shorter, my average rate of change would get closer and closer and closer and closer to 6. So if you're still not convinced, let me summarize these numbers in a table for you and show you what's going on here. So I have the average rate of change on these intervals 1 to 1 plus h, where h is some positive number. Here we're really only considering positive numbers. And I'm letting h go to 0. H started out at 2, and then it was 1, and then it was 0.5, and then 0.1, and then 0.001. And the average rate of change was 8, and then 7, and then 6.5, and then 6.1, and then 6.001. And it looks like my limit is going to 6. So what it looks like we computed is that the limit as h goes to 0 of f of 1 plus h minus f of 1, that's what we kept on computing on the other slide, over 1 plus h minus 1, this looks like it goes to 6. That's what it looks like we're computing. Well, it turns out that this is actually what we're talking about today. This is actually the instantaneous rate of change. This is the instantaneous rate of change. As you take all of these average rate of changes and you consider them over smaller and smaller and smaller and smaller intervals, you get an interval that's so small that it's like just plugging in the point, and that is what the limit is, and that's what we call the instantaneous rate of change. So one symbol for the instantaneous rate of change is f prime, and we, in this example, we're talking about f prime at x equals 1. And what we've seen is that this is approximated by the average rate of change of f on intervals 1 to 1 plus h, where h goes to 0. And so that's precisely, well, I say it's precisely and then I write approximately. That is precisely this limit. As h goes to 0, f of 1 plus h minus f of 1 over 1 plus h minus 1. And notice on the bottom here, 1 plus h minus 1, that's just h. So again, terminology-wise, this is the instantaneous rate of change. And it seems like we can approximate it using average rates of change. Okay, so I want to show you what this looks like. Remember, we have that the average rate of change is represented by a slope, so I want to show you visually what the instantaneous rate of change looks like. So I have a handy Desmos graph that I'll show you of this function that we just looked at. So here is the function f of x equals x squared plus 4x, and I will link to this graph in the description in case you want to go play with it. And you can see I have the point 1, 5 labeled here. That's my point 1, 5. Oh, and now I've just messed it up. There's my point 1, 5. My computer's mad at me. I have this 0.15. Oh, it's still not right. Just one. Just one. There we go. I have this point, and then I have the other point on the other end of my interval. And there we go. I can move it around a bit. So here, let's put this back at 3. And I'll show you the line. So there is my secant line, and I'm going to zoom in a little bit. I'm going to zoom in. So there's my secant line going through those 2 points. And what I can do is I can make h smaller. So here over here I'm dragging h in, and we'll get it so that it goes back in our picture. And see, as I make h smaller and smaller and smaller, the second point is coming in, and all of these secant lines, h can be negative in this picture, all of these secant lines approach this one line that just goes directly through that point. So let's see if I can actually type in h equals 0. Remember, this is a limit, so I don't know if it's going to work. Nope, it's undefined. So remember, in a limit, you can't actually use that. So I'll give ourselves a little tiny h. But what we do have is, if we get rid of that, we do have this line that goes right through that point, and it's called what is tangent. It's called tangent to our curve, which basically means it touches our curve at one point. If I zoom out, you can see that that line is not the same as the curve, but when I zoom way in, woo, this is all over the place. When I zoom way in, that line looks really, really close to the curve. So this is what's called the tangent line. And what we can see is, as our value of h gets smaller and smaller and smaller, come on, as our value of h gets smaller and smaller and smaller, the secant lines approach the tangent line. So the same way that the average rates of change approach the instantaneous rate of change, the secant lines approach the actual tangent line. Okay, so that is a mathematical and a graphical approach to instantaneous rate of change. And again, I will put a link to this Desmos graph in the description in case you want to go play around with it.